Imagine a quiet night, the sky dark and deep like an invisible ocean, with only the faint, steady glow of distant stars keeping watch. Against that vast backdrop, the universe seems to stretch without end, and somewhere within that immensity, a gentle question begins to form. Before all those stars were born, before any galaxy existed, before there was even space for light to travel through, did anything exist at all? For more than a century, science has slowly woven together a portrait of our cosmic history. Cosmologists believe the universe is about 13.8 billion years old. In its earliest moments, everything was compressed into an unimaginably hot, dense state. From that state, space began to expand, matter cooled, light broke free, and from those first simple particles came atoms, stars, and galaxies. The picture of the Big Bang reads like an epic tale of the cosmos. Every observation, from telescopes rooted deep in the ground to satellites drifting silently through space, adds another line to that sweeping story. Yet the moment we open this grand book of cosmic history, an odd blank page appears right at the start. If time, space, matter, and energy all came into being with the Big Bang, then what does before even mean? To say the universe began at a specific moment almost implies there was a larger timeline surrounding it, some vast ruler on which we could mark a before and an after. This question reaches into the heart of how humans think about cause and effect. Ever since childhood, we've known that everything begins somewhere. A tree starts as a seed, a river begins as a stream, a story opens on its first page. So when we hear that the universe had a beginning, the mind naturally takes one more step. What was the universe's seed, its first trickle of water? The spark that switched everything on? But at the boundary between modern physics and everyday intuition, things become harder to grasp. When all of existence is compressed into a state smaller and denser than we can imagine, our two great physical frameworks, general relativity and quantum mechanics, intertwine in ways that resist harmony. And right at that crossroads, the question before the universe stops being something we can answer by simply turning the clock back a few ticks. It becomes a step toward the very edge where our familiar ideas start to dissolve. Perhaps instead of imagining before as an ordinary stretch of time, we must allow ourselves to think differently. Let every clock fall silent, every calendar fade away, every sense of yesterday and tomorrow loosen its grip. Picture not a moment, not an object, but a kind of potential, a state of possibility, a realm of existence so abstract that time as we know it hasn't yet begun to flow. A realm that may not be empty, yet resembles nothing we have ever touched in the small, familiar room we live our lives in on this little planet. It is along that hazy boundary that bold scientific ideas begin to appear. Some suggest our universe is just one bubble inside a far larger reality, where countless other bubbles are born and fade. Others imagine that our universe is only one cycle in an endless rhythm of expansion and collapse. In this landscape, the important thing isn't to pick a single story and believe it must be true. At the farthest edge of our knowledge, every model remains a humble attempt to describe a reality that may stretch far beyond imagination. Each hypothesis is like a scientific fable woven from math, logic, and delicate observations. And under all the formulas lies something deeply human, a desire to know where we came from and where we stand in this enormous cosmic tapestry. A single absolute beginning, an infinite cosmic loop, or something completely different, something outside every familiar picture. We cannot know which, if any, is right. Each possibility carries its own quiet emotional weight, its own shade of wonder. And maybe there will never be one perfect answer that satisfies all intuition. But the journey, questioning, searching, building models, testing them, revising them, enriches our understanding, our imagination, and our humility. In the chapters ahead, we'll explore the major ideas offered by modern physics to approach this question. Each will be unfolded gently, like turning the pages of a slow, lingering story, giving abstract concepts time to settle and become familiar. There is no promise that a final, ultimate truth waits at the last page. Only a soft invitation. Let yourself drift along these scientific stories the way you might drift on a quiet river of thought. Somewhere in the vast darkness of the universe, within all the possibilities of before the universe began, you may find a curious kind of peace, a calm acceptance that so much remains unknown, and that this very mystery is part of what makes the cosmos so deep, so beautiful. On this journey, each idea is not a test, but a small light, just bright enough to soften the night of your thoughts before gently fading into sleep. From the dreamy reflections on the question of whether anything existed before the universe was born, the journey seems to drift naturally toward the first moment science can trace, the moment known by a familiar yet endlessly mysterious name, the Big Bang. It feels as though, after floating through a realm of abstract ideas, we gently touch down on a foothold of modern understanding, where the earliest pieces of the cosmos begin to fall into place. From the hazy region before time itself, we step into the place where time has just begun, like watching a story cross from a blank page into its very first line. And in that first line, the history of everything that would ever exist, including us, was written for the very first time. According to the Big Bang model, the universe is about 13.8 billion years old. That number is not merely a measurement. It is a story told by ancient light, by the faint signals left behind from when the universe was still newborn. If we trace the past far enough, every galaxy, every star, every atom converges into a strange state. Incredibly small, incredibly hot, incredibly dense. A state often imagined as a singular point, though in truth, it was a region of such intense energy that the mind struggles to hold on to it. It wasn't a bomb exploding in empty space. It was space itself swelling outward, carrying everything within it. At that moment, matter and energy reached temperatures and densities far beyond anything a volcano on Earth could produce, and beyond even what the most powerful particle accelerators today can recreate. Within a fraction of a second after zero moment, the universe was a roiling sea of pure energy, where particles and antiparticles flickered into existence only to annihilate each other again. Tiny sparks that vanished as soon as they appeared. Space expanded relentlessly, stretching this energy outward, cooling it little by little, like water settling after being stirred into a frenzy. Within just a few seconds, as the temperature dropped enough for basic particles to stabilize, protons and neutrons began to bind together, forming the first atomic nuclei. This era, known as primordial nucleosynthesis, gave birth to hydrogen and helium, the two lightest elements, in proportions that are still imprinted across the stars today. Their distribution, measured through the light of billions of stars, remains one of the strongest pieces of evidence for the Big Bang model. But the universe was still not transparent. While temperatures remained high, electrons, protons, and photons collided in a chaotic dance, making it impossible for light to travel freely. The universe was a thick, glowing plasma, like a primordial fog, where light was scattered endlessly, unable to move through space the way it does today. Everything existed in a bright, dense world with no stars, no galaxies, no distinct points of light, only a shimmering, turbulent glow. Only when the universe reached about 380,000 years of age did the temperature fall low enough for electrons to bind to nuclei, forming neutral atoms. This event is known as recombination. The moment the last free electrons settled into place around their nuclei, the light that had been trapped for hundreds of thousands of years broke free and began its long journey across an expanding cosmos. That light has traveled for more than 13 billion years and still lingers today as the cosmic microwave background, the oldest signal humanity can observe. From this nearly uniform sea of plasma, tiny ripples in density gave rise to slightly heavier and slightly lighter regions. These microscopic fluctuations, under the pull of gravity, slowly became the seeds of structure. Matter gathered into enormous clouds of gas, and within them, dense pockets collapsed inward, heating up until one day they ignited as the first stars. Those stars, long gone now, were the very first to illuminate the darkness of the universe. As stars formed, gravity pulled them together into larger clusters, then swirling galaxies, then merging galaxies. Over billions of years, from tiny patterns in the early universe, an immense cosmic web emerged, a vast network of hundreds of billions of galaxies stretched across space like interwoven threads of light. This story is not only about the birth of matter, it is also the story of the birth of time and space themselves. In traditional cosmology, time does not exist before the Big Bang. This is not a technical footnote. It is a fundamental shift in how we imagine reality. If time began with the universe, then the idea of before becomes a question that no longer fits. Before the Big Bang does not resemble the before of everyday life. It is a region where our usual definitions simply fail to apply. This realization gives the Big Bang picture a dreamlike quality, scientifically solid, yet filled with a sense of the vast unknown. When we observe the cosmic microwave background, the lingering light from the universe's first act of transparency, it feels like listening to a faint echo from the dawn of all existence. And within that echo lies a quiet peace, a peace belonging to a past far too distant to reach, yet close enough for human imagination to wander through. Even though this picture explains much of the universe's history after its earliest moments, it still leaves a blank space at the very beginning. It shows us what happened right after the first instant, but it says nothing about what came before. As if the story has a brilliant opening chapter, but its front cover has been torn away. And so, when the tale of the Big Bang comes to a gentle close, a natural longing arises. Is there something beyond that missing cover page? The next part of the journey opens into bold, delicate hypotheses, ideas where science attempts to imagine what might have occurred before time began to flow. From here, the story drifts onward, softly carrying us into the chapters about cosmic inflation, an idea with the potential to reshape how we understand the origin of everything. As the picture of the Big Bang gently comes to a close, a quiet pause seems to open between layers of thought. The universe already has a clear history from its earliest traceable moments, from the opaque sea of plasma to the first light that escaped, from the primordial gas clouds to the first stars that pierced the darkness. Yet as soon as we try to hold the entire journey in our mind, a natural idea drifts in, like a small current slipping softly into consciousness. If this is only the first chapter science can read, then where are the pages before it? If time began with the Big Bang, Can we still ask before in the ordinary way we use that word in daily life? Or must the question itself be gently reset at the roots, subtle and deep, as though we're touching the fragile boundary between what can be known and what slips beyond the reach of familiar language? The idea of before the universe is not like questions about the past in everyday life. We can ask what a plot of land looked like before a house was built, or what a region was like before a road was laid. But when we ask, what was before the universe began, even the meaning of the word before no longer holds steady. In modern cosmology, time is not a pre-existing frame supporting all events. Time is one ingredient of the universe, just like space, matter, and energy. If all of these emerged together at the Big Bang, then asking before becomes like asking for the direction north of the North Pole. A question that isn't wrong, but no longer fits the framework in which it was asked. Trying to picture this is sometimes like walking toward the horizon. The farther you go, the farther the horizon stretches, giving the illusion that you might one day touch it. Yet it always remains just out of reach, not because it hides something, but because it marks the limit of your perspective. Before the Big Bang, in today's science, works much the same way. A concept we can contemplate, but not one that fits into the usual definitions. To clarify this, imagine a gentle mental exercise. Picture a globe. As you follow a line of longitude northward, you eventually reach the North Pole, the furthest point in that direction. And once you stand there to ask, what lies further north, is for the question to lose its meaning. Not because the world ends, but because the frame used to define the question has dissolved. In the same way, if time itself was born with the universe, then asking what came before uses a mode of thinking that only makes sense once time already exists. The question demands a context that by its nature has not yet formed. Even so, science does not stop there. Although the Big Bang marks the limit of traditional description, theoretical physicists have sought ways to extend the cosmic picture, ways to reach beyond the point where time loses its familiar definition. Through mathematics, reasoning, and attempts to weave together the two great pillars of physics, general relativity and quantum mechanics, they have built models that supplement or expand the Big Bang, hoping to glimpse what might lie across that boundary. These models do not claim that there was a pre-universe era, but they suggest the possibility that the birth of the universe could be an effect of something larger, deeper, perhaps utterly unlike anything we experience. This does not mean science has found the answer. On the contrary, all these hypotheses are still sketches, like half-open doors into rooms not yet fully lit. They do not recount what definitely happened. They describe what could have happened according to mathematics and the limits of modern physics. Yet even in their uncertainty, they broaden the space of scientific imagination. From models where the universe is one phase in an endless cycle, to ideas of a multiverse where countless worlds arise like bubbles in a vast ocean of energy, to quantum theories where space and time are not smooth at all, but woven from atoms of spacetime. All of them hint at one thing. The question, before the universe, may lead far beyond anything intuition alone can reach. This is why the goal is not to seize upon a single definite answer right away. Instead, the important step is accepting that the question requires a shift in perspective, much like needing a new kind of map when entering a new landscape. If the Big Bang is the beginning of time, then to describe anything before it, we need a different framework altogether, one in which time might behave differently, or might not resemble time as we know it at all. It's similar to rising from the surface of the sea into the sky. The rules that govern water no longer apply, and new rules are needed to describe the motion of wings. In the scientific world, such ideas matter not only for their complexity, but because they remind us that knowledge always has a frontier. And every time humanity touches that frontier, we have the chance to widen our view. Even when these hypotheses turn out not to be right, they serve as small lanterns along the path of discovery, bright enough to illuminate a short stretch, helping us walk a little farther into the darkness of the unknown. And in this unfolding story, the next part brings us to one of the most remarkable ideas about the universe's earliest moments: cosmic inflation, the astonishingly rapid expansion that occurred in a fraction of a second after the Big Bang. Inflation acts as a bridge, carrying science from questions about origins into a broader landscape, one where the possibility of countless universes first begins to appear. And from there, the journey opens into many new pathways, as gently as rivers branching into one another under a quiet night sky. As the story of what the phrase "before the universe" can mean comes to a close, another doorway seems to open softly. The limits of time remind us that many familiar questions suddenly lose their footing when applied to the universe's earliest beginnings. Yet, it is from that very boundary that scientific thought begins searching for new paths. If time cannot simply extend backward before the Big Bang as a river returning to its source, then perhaps our universe is not the entirety of reality. Perhaps what we call the universe is only a small piece of a much larger picture, one in which countless other worlds coexist in a realm we have never touched. That idea is not only a natural continuation of the earlier question. It feels like a pathway unfolding into limitless possibility, a region of imagination where reality may be far richer than we ever assumed. In modern physics, there is a concept both bold and deeply captivating: the multiverse. Its central question seems almost disarmingly simple. Is this universe everything or not? Is everything we observe, no matter how vast, truly the whole, or only a single room within a house so immense that we cannot begin to grasp its scale? The question satisfies curiosity, of course, but it also reflects one of the most serious directions in theoretical physics, where mathematical models, cosmological observations, and ideas about spacetime intersect to create increasingly rich landscapes of possibility. Some theories suggest that other universes may exist, either parallel to or entirely outside our own. Parallel does not necessarily mean next to us, nor separated by a thin, invisible veil. In many models, parallel universes may exist in dimensions that human senses cannot perceive at all. Each universe may carry its own set of physical laws, different constants, and perhaps forms of matter, and even time, utterly distinct from ours. They do not influence one another, do not exchange light, do not overlap, and therefore cannot be observed by any present-day instruments. Yet their possibility does not violate modern physics. In some cases, it is a natural consequence of the equations themselves. To picture this more gently, people often compare universes to soap bubbles. Imagine a large cluster of foam, where countless bubbles connect, overlap, or drift close without ever blending. If our universe is one bubble in that foamy ocean, then right beside it, yet completely unreachable, other bubbles may be expanding with their own histories, their own laws, perhaps even forms of life with conditions we could never sustain. Each bubble in this analogy does not contain air, but an entire reality. Space, time, fundamental particles, energy, even galaxies. It is a simple image, Yet it stirs something deep, a blend of smallness in the face of immensity and gratitude for living in a bubble where the physical conditions allow life to arise. Extending this image, one can imagine that this cosmic foam is not still. Bubbles may grow or shrink, form anew, drift apart, or vanish into regions of space that human language cannot truly describe. Some bubbles may be too cold, too diffuse, or governed by constants that prevent stars from forming. Others may be bright, rich in energy, overflowing with activity. Each bubble is its own story, and among this countless collection of stories, we inhabit a particularly rare chapter, one in which physical constants and initial conditions allow life to contemplate its own existence. Thinking in this way expands our sense of reality far beyond the limits of familiar intuition. Instead of one universe containing everything, we may be living in a crowded neighborhood of universes, each a different home with its own rules. The feeling evokes a deep humility. If our universe is only a fragment of a far larger panorama, then human existence becomes both fragile and astonishing. Every atom forged in ancient stars, every ray of light from distant galaxies, every moment of consciousness becomes a delicate echo in a reality so vast, the mind can scarcely hold it. Though the multiverse may sound at first like the stuff of science fiction, it emerges from serious physical theories. Some inflationary models of the very early universe naturally lead to the creation of countless bubble universes. In other frameworks, the landscape of string theory allows for an enormous variety of spacetime configurations, each corresponding to a possible universe. Even in quantum mechanics, one interpretation suggests that every natural choice creates a new branch of reality, where all possibilities unfold. Each model has its own level of support and debate, but together they open the door to thinking that our universe may not be the only one in existence. This idea is not meant to overwhelm, but to deepen curiosity. Instead of concluding that everything began with a single moment and followed only one path, the multiverse invites us to imagine that many stories may be unfolding in parallel, beyond our observational reach. Like a forest filled with countless trees, each with its own lifespan, we may be standing beneath just one small canopy. Our existence is no less meaningful. It simply becomes more humble and perhaps more poetic when placed within such a vast backdrop. From here, a new story awaits in the chapters ahead. The hypotheses about before the universe do not rely solely on imagining bubbles drifting in a cosmic sea. They emerge from concrete mathematical models, from theories like cosmic inflation, eternal inflation, string theory, the string landscape, and others. Each is an attempt to understand not only how our universe began, but what might lie beyond the limits described by the Big Bang. And in the next part, the story will lead us into cosmic inflation itself, a phase of explosive expansion, like a single breath that stretched space in an instant. From that idea, the possibility of countless universes begins to take clearer shape, and the journey continues in the quiet of the night, where every thought can drift gently like a breeze moving across an endless cosmos. As the idea of the multiverse softly fades, another current of the story seems to open on its own. The quiet image of cosmic bubbles drifting through an ocean of spacetime has already planted a sense that reality might be far larger than the night sky we see. But to understand why so many scientists take this possibility seriously, we need to return to a very special moment. The moment just after the Big Bang, when the universe had only just begun and was still in its most fragile state. It was in that fleeting era that a powerful, elegant, and surprising idea emerged. An idea that could explain why the universe is so flat, so uniform, and so astonishingly vast. This idea is cosmic inflation, a remarkable chapter that science treats as the mysterious preface to the story of reality itself. Cosmic inflation is the hypothesis that immediately after the Big Bang, the universe went through a brief phase of explosive expansion. This phase was so short that it lies beyond ordinary intuition, shorter than a blink, shorter than the time it takes a photon to cross a grain of dust. In that instant, space stretched so rapidly that every point in the universe was pulled apart by factors of billions. This event was not a loud explosion, nor a burst of blinding light. It was a silent expansion, without sound, without collisions, simply space itself unfolding at a speed far beyond imagination. To form a simple picture, imagine the universe at that moment as a bubble nearly as small as a point, suddenly puffed outward. But unlike a balloon inflated by breath, the cosmic bubble expanded so quickly that words like "too fast" hardly capture it. In a fraction of a second, its size increased dramatically, from something nearly zero to a space large enough to hold hundreds of billions of galaxies. The image is simple, yet it conveys the extraordinary nature of inflation. A transformation so sudden and so immense that its imprint would shape the universe forever. What makes inflation compelling is that it was proposed not to embellish the universe's origin with a dramatic moment, but to solve several puzzles that had baffled cosmologists. One of them is the horizon problem. When we observe the cosmic microwave background, the oldest light still traveling through space, we find it almost perfectly uniform in temperature, even across regions so far apart that they could never have exchanged a signal at the speed of light since the Big Bang. Why would areas billions of light years apart be so similar, as if they once sat side by side? Inflation suggests that before they were stretched apart, they were side by side, close enough to share the same temperature. The rapid expansion pulled them to distant corners of the sky, but the imprint of their early closeness remains. Another puzzle is flatness. Observations show that the universe today is astonishingly flat. Parallel lines stay parallel across cosmic distances, and measurements of spacetime, geometry leans so close to Euclidean that it seems almost miraculous. Yet such near-perfect flatness is extremely unlikely unless something smoothed the universe early on. Inflation serves as that smoothing mechanism. When space expands at immense speed, even a tiny curvature becomes diluted, just as inflating a curved balloon to the size of a planet would make its surface appear flat. Thanks to inflation, the present-day universe is naturally flat without requiring exquisitely fine-tuned initial conditions. Inflation also acts as a gentle magic wand that smooths the young universe. Tiny fluctuations in density, microscopic ripples in the early plasma, were stretched outward and became the seeds for galaxies to form later. Without inflation, these small ripples might have been too small to grow into the grand cosmic structures we see today. In this way, inflation is both a scientific explanation and a beautifully fitting piece of the universe's story. When imagining this moment, space does not erupt like fireworks. No sound rings out, and no bright flash bursts forth. There is only a quiet expansion, as if a serene lake were being stretched outward in every direction. Nothing in our daily experience maps perfectly onto this idea, but one might imagine it as an invisible river swelling, flowing outward silently, carrying within it the seeds of galaxies, of light, of matter, of the future. It was an event without noise, yet powerful enough to shape every detail of the cosmos. And in an intriguing way, cosmic inflation is the very starting point of the bold multiverse ideas from the previous chapter. If inflation can happen once, it can happen more than once, perhaps in different regions of a space larger than what we can observe. Some models suggest inflation does not end everywhere at the same time. Instead, it stops in certain patches, forming the bubble universes we imagined earlier. In other patches, inflation continues, causing the surrounding space to keep expanding endlessly. As this process repeats, we are left not with one universe, but countless new universes, each formed in its own pocket where inflation came to a stop. This is why inflation is not merely a chapter in cosmology. It is the gateway to even bolder ideas about the birth of other universes. From this silent, spreading expansion, cosmic bubbles might arise and drift through an ocean of space-time. And when we view inflation through this lens, it becomes more than an explanation of the past. It becomes a doorway to possibilities far beyond what the Big Bang alone ever described. In the next part, the story will delve into one of inflation's most striking consequences: eternal inflation, a scenario in which expansion never fully ends, and in which bubble universes may truly be born as a natural outcome. In that picture, the universe does not have a single beginning, but countless beginnings, countless bubbles of reality, each carrying its own story. And from there, the journey opens further still, as gently as ripples moving across an infinite cosmic sea. As the picture of cosmic inflation comes to a gentle close, it feels as though we're still standing at the threshold of a vast doorway. That sudden, silent expansion was not just the first brushstroke in the universe's history. It was a delicate piece of the puzzle that explains many of the strange features of the reality we now live in. But inflation is captivating not only because of its elegance. What makes it one of the central ideas of modern cosmology is the power it carries to answer questions that once seemed impossible to solve. And so, the story drifts softly into another realm, one where mysteries and clues meet, where inflation becomes not just a beautiful concept, but a coherent explanation for the universe's most puzzling traits. One of the biggest mysteries inflation resolves is the horizon problem. When we observe the cosmic microwave background, the ancient heat map left over from when the universe was about 380,000 years old, we find that its temperature is almost perfectly uniform across the entire sky. No matter which direction we look, the differences are tiny, about 1 part in 100,000. At first glance, this seems ordinary, but thinking more deeply reveals something strange. Regions of the universe that are tens of billions of light-years apart could never have communicated, because even light, the fastest messenger in the universe, has not had enough time to travel between them since the Big Bang. So how did they end up with the same temperature, as if they once sat side by side and quietly agreed on a shared value? Inflation tells a simple, coherent story. Before space was stretched to enormous size, every point in the universe was once extremely close. They had time to reach thermal equilibrium. Then inflation occurred, pulling those regions apart so quickly that today light cannot bridge the distance between them. Yet the imprint of their early uniformity remains. In this way, inflation explains the smoothness of the CMB not through a miracle, but through the fact that the young universe was once far smaller and had time to settle before it ballooned outward. Another intriguing puzzle is flatness. Observations show that the universe is astonishingly flat, so flat that precise measurements from satellites like Planck and WMAP indicate space-time is nearly perfectly Euclidean. If the universe had even a slight curvature early on, that curvature would have grown with time, making today's universe either strongly positively curved, like the surface of a sphere, or negatively curved, like a saddle. Instead, we find ourselves in a universe that is remarkably, almost unbelievably flat. Inflation explains this naturally. When space is stretched by enormous factors in an instant, any tiny curvature is diluted to near invisibility. Just as a huge balloon looks flat to someone standing on its surface, inflation flattened space-time by stretching it beyond any detectable curve. Inflation also adds something essential to the story of structure. It creates the tiny ripples in the density of matter that would later grow into galaxies, clusters, and cosmic webs. These ripples began as quantum fluctuations, subtle tremors occurring on scales smaller than the smallest particles. As space expanded rapidly, these tiny fluctuations were stretched outward, becoming faint variations in density across the young universe. Those slight differences eventually became the seeds from which all large-scale structure emerged. Without inflation, these quantum ripples might have been too small to form anything like the galaxies we see today. And the cosmic microwave background is where we see the first hints of this. In the CMB map, there are tiny bright and dark spots, minuscule temperature variations whose shapes and patterns match precisely the predictions of inflation. They resemble grains of dust on a vast fabric, tiny, subtle, but powerful evidence of the rapid expansion that happened billions of years ago. That image, simple as it is, feels like a faint echo from a time when the universe was still a smooth cloth being stretched out. If the early universe were a piece of fabric, inflation would be the invisible hands pulling it taut. On the surface of that fabric, small ripples, quantum fluctuations rolled gently. When the fabric was stretched incredibly fast, those ripples grew, carrying delicate patterns that would later become the architecture of the cosmos. One day, the slightly denser regions became shining galaxies, while the slightly thinner regions became the vast voids between superstructures. From invisible microscopic tremors, the entire cosmic tapestry was woven, as if nature's hand had quietly left the signature of inflation in every thread. With all these details, inflation becomes more than a hypothesis. It becomes a deeply persuasive explanation for some of the universe's greatest mysteries. It shows that what seemed impossible, the uniform temperature, the near-perfect flatness, may in fact arise from a natural, elegant, and profoundly harmonious process. But the story doesn't end here. The basic version of inflation explains much, but there is another, even bolder variant: eternal inflation. If inflation can happen once, could it continue forever in some region of a larger spacetime? If so, it would create countless universe bubbles, each forming a new cosmos of its own. And if this picture is right, the idea of the multiverse is not just a metaphor. It may be a natural consequence of inflation itself. In the next part, the story will guide us into that idea, a realm where expansion never fully ends, and where new universes may emerge like quiet sparks appearing across an infinite sea. There, inflation does not merely explain this universe. It opens the door to a vast, shimmering landscape of other worlds. And the journey will continue, drifting as softly as the last ripples moving across the primordial cosmic fabric. As the mysteries solved by inflation begin to unfold, a feeling arises, as though we're standing at the edge of a new horizon. Inflation not only made the universe uniform, flat, and structured in the way we observe today, it also hints that the universe's history may be far more intricate than the classical Big Bang picture suggests. The ripples of quantum fluctuations, stretched out by that rapid expansion, left their marks on the ancient microwave background, and later blossomed into galaxies. Yet when we look deeper into the nature of inflation, a quiet question begins to surface. What caused inflation to stop? And what ensures that it stopped everywhere at the same time? That question brings us to one of the boldest ideas in modern cosmology: eternal inflation, in which expansion never truly ends. In the familiar picture of inflation, the early universe swelled rapidly, and then the process stopped, leaving space calm enough for matter to cool and galaxies to form. But in deeper models, inflation does not occur uniformly. Instead, it is driven by a special energy field called the false vacuum, a high-energy state that acts like a kind of pressure pushing space to expand. And this false vacuum does not decay all at once. Imagine the vastness of space as a sea of energy. In some regions of this sea, the false vacuum decays, like a sudden patch of calm appearing on a turbulent surface where waves cease to roll. When the decay happens, it releases energy that forms matter, creating a universe like our own. But in other regions, the false vacuum remains, continuing to force space into inflation. Space in those regions keeps swelling, stretching endlessly forward into the future, as if parts of the cosmos are still living in their earliest moment. This uneven decay creates the idea of eternal inflation. In this picture, the universe does not swell and then stop everywhere at once. Instead, it becomes a kind of cosmic machine. Some parts have stopped inflating and formed bubble universes like ours, while other parts keep expanding without pause. Each time a tiny region of the false vacuum decays, it creates a new bubble, a new universe, with its own time, its own space, its own history. Meanwhile, the surrounding energy sea continues to balloon outward, making room for countless more bubbles to be born. To visualize this more clearly, imagine space as an infinite rug stretching in all directions. On this rug, tiny spots begin to appear where inflation stops and a universe forms, each spot expanding inward, shaping its matter and structure, much like our universe once did. But the larger rug does not stop stretching. It keeps expanding without limit, carrying those tiny spots farther and farther apart. And as it stretches, new spots appear, each one a seed of a new universe, a story of its own within the vast ocean of spacetime. The universe we know, with its hundreds of billions of galaxies, may be just one inflation-ending region inside a much larger, perhaps infinite expanse. And in that larger expanse, countless other cosmic bubbles drift, some as large as ours, some larger still, some smaller, depending on how and where the false vacuum decays. Some bubbles may have different physical constants. Some may have no stars, no light, no stable matter. Others may be so energetic that life could never arise. All of these are possibilities hinted at by the equations of eternal inflation. What makes this idea both dreamlike and persuasive is the enduring nature of the process. Because the false vacuum decays only region by region, there are always places where inflation has not stopped. These regions continue expanding forever into the future, providing endless opportunities for new bubbles to form. While a bubble like our own evolves, forming stars, galaxies, planets, and cycles of time, the parent universe around it keeps stretching, quietly making room for new stories to begin. Each bubble may have a finite lifetime, but the larger expanding backdrop that births them has no ending, a boundless flow of expansion. A small note in cosmology is that although eternal inflation extends infinitely into the future, it does not necessarily stretch infinitely into the past. The process may still require an initial beginning, but that detail is often kept gentle, so the story does not become too heavy for imagination. What matters is not finding the absolute first moment, but grasping the rich structure and vast possibility that this idea offers. If inflation is the opening chapter of the universe's history, then eternal inflation is like a machine operating outside the book, endlessly printing new volumes, each a universe of its own. A softer image might be an invisible loom, weaving thread upon thread of energy into separate worlds. One bubble forms, then another, not in the rhythm of human time, but in the quiet rhythm of a cosmic mechanism that never tires. A story without a final page, in which every new page is itself a new reality. This idea not only expands science, it carries a kind of hazy beauty, the beauty of the infinite. It lets us feel our existence as a tiny part of a reality so immense it resists comprehension, while also reminding us how extraordinary it is that we live in a bubble where light, life, and consciousness were able to form. And from this engine of eternal inflation, many other hypotheses about what came before our universe arise. Some suggest that other universes may drift beyond our sight. Others imagine earlier bubbles forming and fading before ours was born. From here, the story will lead to the bubble multiverse model, where our universe is but one among countless others. But before arriving there, eternal inflation lingers softly, like the gentle, steady hum of a machine weaving infinite worlds into the quiet depths of cosmic night. As the idea of eternal inflation settles, another image drifts in softly, as if it were the natural continuation of the story. If expansion can persist forever in distant regions, and if the false vacuum doesn't decay uniformly everywhere, then each small region that escapes inflation becomes a reality of its own. Other regions remain in the expanding state, waiting for the moment they too will decay and give birth to new universes. From this gentle but persistent mechanism, a larger picture emerges, the picture of the bubble multiverse. It isn't a sudden twist, but a natural pathway extending from eternal inflation, as though the universe were quietly whispering its story outward into infinite depth. In this view, our universe is just one of countless bubbles formed when inflation ended locally in some region. The hypothesis suggests that when the false vacuum decays at a point in the larger spacetime, the energy it releases becomes the source of matter and radiation in the newly formed universe. Though tiny in the context of the ever-expanding parent space, that event is a local Big Bang, a complete beginning for a self-contained universe, with its own space, its own time, its own history, its own conditions, and possibilities found nowhere else. Imagine an infinite sea of expanding space. In that ocean, countless small bubbles appear, each potentially growing to span hundreds of billions of light years, each a fully formed universe. These bubbles drift apart forever, never touching, because the space between them is expanding faster than light. Not because they are moving, but because the fabric of space itself is pulling them away. Like droplets of dew on a stretching sheet of glass, the bubbles float, solitary, isolated. Though innumerable, each bubble experiences its own flow of time, sharing no light, no information, no gravity with the others. In the bubble multiverse picture, the strange truth is this: the bubbles are not identical. On the contrary, each might possess a different set of physical laws, depending on how the false vacuum decays. Physical constants, like the speed of light, the mass of the electron, the strength of gravity, may vary. Even the types of particles, the number of spatial dimensions, or the fundamental forces could diverge from what we know. This creates a nearly endless landscape of possibilities. Universes with no stars. Universes where matter is too fragile or too rigid for anything stable to form. Universes so saturated with dark energy that galaxies never emerge. And then, scattered like rare grains of sand in an endless desert, a few universes with just the right conditions, like ours, where stars can shine, planets can form, and life can appear. Imagining these cosmic bubbles makes us realize that a universe like ours, where the physical constants appear finely tuned for life, may not require a miracle or special preference from nature. It may simply be one outcome among a vast ocean of possibilities. Just as scattering billions of seeds will yield only a small number that land in perfect soil, our universe may be one of the lucky few. That luck does not make our existence less meaningful. It makes the universe feel larger, and our presence within it more wondrous. Seen this way, the bubble multiverse is an extension of eternal inflation. As the larger space keeps expanding forever, small regions continually fall out of inflation and generate new bubbles. Those bubbles form their own structures and drift so far apart that no connection remains. And this process occurs not once, but infinitely many times. This is no longer the story of a single universe born from a single Big Bang, but the story of a super-universe, a vast cosmic foam where countless Big Bangs sparkle like tiny lights in endless darkness. Placing our universe within that context evokes a special feeling. On one hand, we sense the near unbelievable smallness of ourselves within an infinite sea of realities. On the other hand, a gentle sense of gratitude emerges. A universe like ours, where galaxies, stars, and a small blue planet can exist, may simply be the outcome of a fragile probability within an ocean of possibilities. And we are living inside one of those rare bubbles. That luck does not diminish the value of our existence. It makes it even more precious. Although this idea is vast, it is not merely imagination. It arises from inflationary models, from quantum physics, and from the structure of the equations that describe the early universe. Even if unconfirmed, it reflects a deep truth. Reality may be far more complex than the classical picture once taught in classrooms. And perhaps it is this complexity that gives the story its delicate beauty, making it feel like a scientific myth, one not told around a campfire, but contemplated beneath the night sky. And as the bubble multiverse fades gently into the distance, the journey naturally leads to another wondrous chapter: string theory and the concept of the cosmic landscape, where the number of possible universes is not merely infinite in count, but infinite in form. In the next part, we will step softly into a world where every particle, every force, and every version of reality may be nothing more than tiny vibrations of invisible strings, an image so strange, yet so beautiful, it's hard to look away. As the image of the bubble multiverse has barely begun to fade into the vast openness of imagination, another gentle and profound question begins to rise. If each universe bubble can have different physical laws, what determines those laws? What lies at the most fundamental layer of reality, where every particle, every force, and every transformation begins? This question flows like a small stream branching from the great ocean of the multiverse, guiding us deeper into the microscopic fabric of existence. And here, a strange yet exquisitely elegant idea emerges, one that views the universe not as a structure built from rigid point-like particles, but from tiny vibrating strings, trembling like the primordial notes of existence itself. This is string theory. String theory begins with a simple assumption, yet one powerful enough to change how humanity perceives the world. Instead of being zero-dimensional points, the fundamental building blocks of reality are incredibly tiny, one-dimensional strings, filaments of pure energy, thinner by billions of times than anything we could ever observe. These strings are never still. They vibrate, and the way a string vibrates determines the type of particle it becomes. One mode of vibration produces an electron, another produces a photon, and another gives rise to the graviton, the hypothetical particle that would carry the force of gravity. If the universe were an enormous symphony, then each fundamental particle would be a musical note. Strings vibrating at different frequencies create different tones, much like the strings of an instrument. Put all these notes together, and you get the symphony of nature, the music of space, of light, of gravity, of reality itself. Every proton, every photon, every electron, even the carriers of forces, are simply different expressions of one underlying object, the string. There is a surreal beauty in this idea. Properties that seem unrelated, the mass of a particle, the strength of a force, the character of light, are all results of the way these tiny strings vibrate. A single underlying system expressing itself in countless forms. Seen this way, reality feels unified, fluid, and far more graceful than earlier mechanical pictures ever suggested. But this isn't even the strangest part. String theory also suggests that the world does not consist solely of the three spatial dimensions we experience daily. For the theory's equations to work fully, the universe needs 10 dimensions in one version and 11 in the expanded framework known as M-theory. The three large dimensions we move through are just the visible surface. The others are compactified, folded into tiny, complex shapes at every point in space. Imagine that every point in space is not a simple location, but a miniature multidimensional structure the human eye can't perceive, full of curves, twists, folds, pockets, and hidden loops. Strings weave through these structures, vibrating along paths defined by the geometry of the compact dimensions. The specific shape of these hidden dimensions determines the physical constants of a universe. If those dimensions curl one way, one set of laws emerges. If they curl another way, an entirely different universe is born. This image carries a delicate, almost dreamlike quality. Space is not merely emptiness. It is a layered fabric. Hidden within it are tiny chambers where strings twist, stretch, and hum, producing the frequencies that shape everything we observe. The richness at the microscopic level gives rise to the diversity we see on the cosmic scale. To soften the picture even more, imagine the universe as a giant guitar. Each particle is one of its strings. But these strings do not simply vibrate in three familiar dimensions. They resonate within extra curled-up dimensions, folded deep inside the instrument. Each note's sound depends not only on the length of the string, but on the intricate shape of the guitar's interior. A small twist or hidden contour deep in the wood can change the tone. Likewise, the shape of hidden dimensions determines all the properties of particles and forces. This idea transforms the universe into something deeply artistic. No longer a rigid diagram of fundamental particles, it becomes a piece of music, an intricate, multi-dimensional sculpture where everything is connected through tiny, trembling vibrations. And this ties back beautifully to the earlier picture of bubble universes. If each bubble can have different laws, then string theory provides the foundation for such variation. Change the shape of the hidden dimensions, and you get a different universe with different physics, different particles, different possibilities. It opens the door to a limitless landscape. Even though string theory has not yet been proven directly, it offers a rare sense of harmony in theoretical physics, a unification of matter, energy, gravity, and the geometry of space. It is not merely a mathematical tool, it is a new way of seeing reality, soft, intricate, and suffused with the aesthetic rhythm of nature. In the quiet darkness of the universe, where only the tiniest vibrations of existence remain, string theory feels like a gentle invitation. Listen to the background music of the cosmos, a melody played not by any instrument, but by the very fabric of space and time. And from here, the journey leads naturally into the next idea, the world of branes, multi-dimensional surfaces, where not just strings, but entire higher dimensional entities may form the foundation of reality. Another chapter, connected and gentle, waits ahead, as the picture of string theory lingers with the soft resonance of microscopic vibrations. Another question slowly rises in thought. If strings are the fundamental units, and if they can vibrate in countless ways within hidden dimensions, then could space itself contain more forms of existence than we ever imagined? The idea that particles are not points but strings already shakes our familiar intuition about reality. And as we venture deeper into this theory, what comes next is even more astonishing. Strings are not the only objects that can exist. In the multidimensional setting suggested by string theory, there are also higher dimensional surfaces, vast extended structures like cosmic sheets, called branes. From this foundation, a new chapter opens, moving gently and deeply, carrying our imagination into a space broader than anything strings alone could describe. In the extended version of string theory, M theory, not only one-dimensional strings exist, but also higher dimensional objects. A two-dimensional brane, a three-dimensional brane, even a nine-dimensional brane can appear depending on the geometry of space. Seen from this perspective, our universe, with its length, width, and height, may itself be a three-dimensional brane, a three-brane floating within an 11-dimensional expanse. Every star, every galaxy, every planet, and even we ourselves reside on this brane. When we look outward, when we see the Milky Way, when we admire the light of stars thousands of light years away, everything we see is contained within this three-dimensional membrane that we inhabit. Beyond this brane surrounding us may lie hidden dimensions curled and folded like tiny ridges no human eye will ever touch. To soften the idea, imagine our universe as a thin, invisible sheet drifting in a much larger space. And right beside this sheet, separated by only a tiny distance, but along a direction we cannot move, there could be another sheet just as vast, containing its own universe. If these two sheets are two 3D branes, then each is a self-contained universe. They lie close together, but never touch, never influence one another in any familiar way. If someone lived on the neighboring brane, they would never see us, just as we would never see them. Light cannot cross the hidden dimension separating the branes. Gravity may be limited, and no information can pass between the worlds. This image evokes a feeling that is both mysterious and gentle. Perhaps right alongside our universe, just a tiny shift away in the 5th, 6th, or 7th dimension, lies another world. A world with different stars, different physical laws, perhaps even a different flow of time. Not billions of light years away, but as close as 2 pages in the same book. And yet, because we can only move through the 3 familiar dimensions, we can never step into that world. We can only imagine it, like someone dreaming of a door that does not belong to any room in the house they know. In this context, the idea of many brain world universes feels completely natural. If one three-dimensional brain can exist, why not thousands, millions, or an uncountable number, drifting through a higher dimensional space? Each brain could hold a complete universe with its own physical rules. Some brains might resemble ours. Others could be entirely different. There could be brains where gravity is stronger, brains where light moves more slowly, or brains where electromagnetism does not exist at all. Such possibilities emerge the moment we allow space to have more than 3 dimensions. This image also invites us to reflect on how isolated our universe might be. If the cosmos is a drifting brain, then no matter how far we look, we are only scanning along its surface. We never see beyond it. We never glimpse the full shape of the higher dimensional space. We are like creatures living on a sheet of paper, unaware of the dimension in which the sheet itself is floating. This realization brings a sense of humility, yet it also enriches our imagination. Reality may be vastly larger than anything our senses can grasp. The concept of brains also forms the basis for several hypotheses about what happened before the Big Bang. If 2-3 brains can drift through a higher dimensional space, then sometimes they might come close, collide, and separate. For some physicists, such a collision could be the event that created our Big Bang. In this view, the universe did not emerge from absolute nothingness. It was born from the meeting of 2 cosmic membranes, releasing immense energy and igniting time, space, and matter as we know them. This idea becomes the heart of the next chapter, Ekpyrotic Cosmology, where the story of cosmic collision is told in its softest, most vivid form. Before we step into that chapter, a gentle feeling lingers after our journey through the brain world. Existence may be far more intricate than what our eyes reveal. The past, the present, the future, and the entire history of our universe may be only a small patch on a vast structure, where countless brains drift silently and mysteriously through a higher dimensional expanse. Thinking of this, we feel both small and simultaneously as though we are standing at the threshold of a picture broader than anything we have ever dreamed. And at that threshold, the story of brain collisions, the sparks that could have created our universe, is waiting to be told next. That will be the next step in the journey to explore what might have existed before the universe began. As the idea of higher dimensional brains drifts through the imagination, like vast cosmic sheets floating in an 11-dimensional space, a quiet question begins to unfold. If these brains can exist side by side, and if each brain can cradle a universe with its own set of laws, then what determines those laws? What decides that our universe has gravity as strong as it is, that photons carry light, that electrons have the familiar mass we know, and that the cosmological constant is small enough for galaxies to form? The deeper we walk into the foundations of string theory, the more natural this question becomes. Because the very structure of the hidden dimensions opens into a landscape so immense it feels almost without boundary. And that landscape carries a name that is both poetic and mysterious: the string landscape. In string theory, the hidden dimensions are not merely curled up like tiny tubes or loops. They can fold, twist, braid, and weave together in trillions upon trillions of different ways, forming microscopic shapes so intricate the human mind can hardly picture them. Each way of curling these dimensions produces a different energy configuration, a different vacuum state, and from that, a different set of physical constants. If the dimensions curl one way, gravity might be stronger. If they curl another way, the electron might be heavier. If a subtle curve in a hidden direction shifts even slightly, atoms might never become stable at all. These possibilities are not arbitrary. They're prescribed by how space itself folds in the smallest layers of reality. The astonishing part is the number of possible foldings, a staggering 10,500. Even when whispered slowly, that number still stretches far beyond anything the mind can comfortably imagine. If each folding corresponds to a possible universe, then the string landscape is like a map with 10,500 destinations, each one a complete universe with its own physical rules. However wide our imagination might be, that ocean of possibilities spreads far past any night sky we have ever looked upon. Within that grand picture, our universe is simply a small valley among countless peaks and valleys of energy, one of the rare places where the physical constants rest in just the right range to let stars burn, planets form, and life evolve. A valley not so shallow that matter becomes chaotic, not so deep that the universe collapses at once, but resting at exactly the depth needed to sustain a stable world. Like a pocket of fertile soil nestled within towering mountains, this valley allows life to take root, while countless others lack the conditions to do the same. This image can make anyone feel small within the wide sea of reality, yet it also brings a soft beauty, a sense of how precious this world truly is. If the string landscape is an enchanted forest with uncountable trees, then our universe is but one tree among them, and we happen to live on a branch where the light is just right, where water can seep in, where life can cling and grow. One tree out of many, yet the only one we know, the only one we can call home. This naturally leads to an idea known as the anthropic principle. If there are countless possible universes, then it isn't surprising that only a very small number of them can sustain life. And because we are here to ask this question, we must, of course, be in one of the universes where life can arise. It's not pure luck. It's a kind of necessary selection. Just like scattering millions of seeds across the ground, most fall on dry dirt, stones, or deep water. Only a few land in rich soil. Our existence is like one of those few seeds, not a supernatural miracle, but the natural outcome of an enormous range of possibilities. The string landscape expands the idea of a multiverse in a direction different from eternal inflation. In eternal inflation, countless universes appear because space keeps expanding and breaking apart. In string theory, countless universes arise from the ways hidden dimensions curl and fold. Two different paths leading to the same vast picture. Reality may hold far more possibilities than we ever imagined. And perhaps long before our universe formed, this immense landscape of possibilities was already there. Each string configuration, each curled dimension, each energy valley waiting for a universe to be born. That feeling brings us gently back to the softness of the story. Reality may not be a straight line from the Big Bang to today. It may be a grand garden stretching endlessly, with countless little pathways branching outward, each one leading to a world. And our universe is just one of those paths, beautiful in its own way, shaped just right for life to look up at the sky and wonder where it came from. And as the story of the string landscape comes to a close, another chapter quietly invites us in. A chapter about the collisions between brains, about the sparks that may have ignited the Big Bang, about the idea that the universe might not have been born from nothing, but from a colossal touch between two vast membranes in higher dimensional space. From here, we'll gently step into the world of Ekpyrotic cosmology, where the story of the universe's beginning opens in a way both unexpected and profoundly moving. As the door to the string landscape softly closes, the echo of an endless forest of cosmic possibilities still drifts through the mind. In that quiet scenery, each universe is a valley, a resting place, a configuration of hidden dimensions curled in their own unique ways. And from the sheer infinity of these possibilities, another question rises, tender but profound. If the microscopic structure of space can determine the constants of each universe, then what might have laid the groundwork for the appearance of space itself? If each universe is a valley within this vast landscape, what guided our universe into the valley it occupies today? That question, like a silent breath, leads us back to the idea of branes, multi-dimensional membranes that form the stage for existence. And from the meeting point between the string landscape and the world of branes, a bold hypothesis emerged. Ekpyrotic cosmology, a story of collisions across higher dimensions, where the Big Bang is not the absolute beginning, but the aftermath of a cosmic touch. In the Ekpyrotic hypothesis, the origin of the universe does not begin with a singular point crushed into infinite density, as the classical Big Bang describes. Instead, the story begins with two enormous branes floating in higher dimensional space, like two invisible, endlessly stretched planes. These branes drift quietly toward one another over time, like two parallel worlds slowly gliding through an 11-dimensional realm we cannot perceive. As they draw closer, the primordial universe begins to contract, cooling and calming, silent as a lake before sunrise. When the branes finally come close enough, a single event occurs, a collision, vast beyond imagination, but not explosive in the way we often picture. Instead, it resembles a spark flaring in the dark, igniting space, transforming the energy of impact into matter and radiation. That spark is the Big Bang, not a birth from nothing, but the culmination of a long, orderly process. Two branes drifting, approaching, then touching. From that touch came every photon, every atom, every galaxy, every world. The image carries a quiet elegance, imagining two colossal membranes gliding toward each other in a silent void. One can almost sense a gentle rhythm, not loud, not abrupt, but steady and patient. And in the moment they meet, all the energy accumulated during the contraction transforms into light and heat, like a soft pop blooming in the night, subtle yet powerful enough to open a new era for all of space. What makes the Ekpyrotic model remarkable is that it doesn't portray the Big Bang as the beginning of everything, but as a big bounce, a cosmic rebound. Before that burst of light, the universe wasn't empty. It existed in another form, in a slow and cooling phase of contraction. When it reached its final point, instead of collapsing into an infinite singularity, it bounced back through the collision of the two branes. This gives real scientific meaning to the concept of before the universe. Before the Big Bang came a different universe, whose conditions may have left subtle fingerprints on the cosmos we see today. This hypothesis also reveals a graceful overlap between particle physics and cosmology. Concepts like branes, hidden dimensions, and string structures, usually reserved for the microscopic world, become the foundation for describing the birth of the entire universe. When two branes collide, the quantum-scale energies of strings transform into the most immense event ever witnessed, the beginning of space, time, and matter. A union between the very small and the very large, between microscopic vibrations and the nuclear fires of stars. Seen in this light, the Big Bang is no longer an absolute boundary between nothing and existence, but a link in a cyclical chain of cosmic transformations. That collision may not have been the first. There may have been cycles before it. Branes drifting together, meeting, creating a universe, then separating, drifting again, and creating another. If that is true, then time is not a single arrow, but a slow breathing of cosmic membranes, each breath lasting trillions of years. Such an idea does more than offer scientific speculation. It stirs something quietly emotional. It doesn't merely answer what happened before the Big Bang. It invites us to imagine that the universe may have lived, changed, and been reborn many times before we ever arrived. It makes the notion of before the universe feel almost familiar, like an older chapter in an endless book we've only begun to read. Within the stillness of the Ekpyrotic picture lies a distinctive beauty. The slow drift of two branes, the gentle touch that gives birth to light, and the idea that the universe began not from a point, but from a process. And as this chapter closes, the next step emerges softly. If a contracting phase preceded the Big Bang, if everything rebounded from a collision, then perhaps something similar happens in other models of quantum cosmology as well. That thought leads us toward the next story, the Big Bounce in loop quantum gravity, where space and time themselves can contract and spring outward like a cosmic coil. Another journey, gentle yet profound, waits to be told. As the picture of Ekpyrotic cosmology gently comes to a close, a faint afterglow lingers in the mind. If the Big Bang was simply the result of a touch between two vast branes, if that burst of energy came from a colossal collision in higher dimensional space, was that touch a once-in-eternity event? Or was it merely a moment in an endless cycle of approaches and separations between those branes? The idea of a Big Bang born from a collision is already strange, but when we listen more closely, the story stretches even further. Perhaps the universe has not simply been born once, but has passed, is passing, and will continue to pass through repeating cycles, like the slow, deep breathing of a vast living entity that transcends anything we usually understand. In the cyclic version of the Ekpyrotic model, developed through the work of Steinhardt and Turok, the Big Bang is not an absolute beginning, but a transition point between cycles. After the branes collide, giving rise to the hot, radiant universe we live in, they do not remain pressed together forever. They separate and drift apart again in higher dimensional space. As they part ways, our universe continues through a long era of expansion, thinning out matter, cooling the cosmos, and pulling galaxies farther and farther from one another. But then, like two colossal curtains drawn back by a faint yet persistent tug, the branes begin their slow return toward each other. The span between these encounters is not a few million or even a few billion years. It may stretch across trillions of years. Throughout that vast interval, our universe will keep expanding, dimming, cooling. Stars will extinguish one by one, galaxies will dissolve into lonely stars, then into cold remnants. And yet, even as everything grows sparse and quiet, the silent motion of the branes continues. They drift closer, very slowly, but without pause. And someday, in a future far beyond human imagining, when the distance between them shrinks to its final limit, another collision will take place, once again igniting a flash of creation, another Big Bang, and a new universe rising from the ashes of the one before. This image feels like the breath of an infinite being. The universe expands like a long, deep inhale, then contracts and bursts into light, a renewed exhale of cosmic energy. Each breath lasts trillions of years, so slow that no human could ever sense the rhythm. But if we were to compress time, we could imagine the universe inhaling and exhaling in steady cycles, like the alternation of night and day, spring following winter, life ebbing and returning, only on the scale of reality itself. Seen this way, our Big Bang was not the first. There may have been countless Big Bangs before it, each one giving birth to a universe filled with stars, planets, and perhaps even life. Each universe would grow old, thin out, cool, and fade into darkness, making room for another collision, another burst of creation. In this cyclic model, time is not a straight line from past to future. It is an endless circle. Before our universe came another, and before that one, yet another, stretching back without a true beginning. This idea carries a deep philosophical beauty, soothing the mind with the rhythm of the universe itself. It suggests that endings are not annihilations, but transitions in a cycle of rebirth. Like seeds resting in winter soil before rising again in spring, a dying universe simply clears the way for the next one to bloom. And within that eternal cycle, we are living in just one chapter of an endlessly long story, gentle and continuous as waves folding against a shore. The thought of a cyclic cosmos brings an unexpected comfort. It paints a picture of perfect continuity. Nothing is truly lost. Everything moves from one phase to another. If the branes can meet and part again, then our universe is not confined to a single moment of expansion. It becomes part of a greater rhythm, a cosmic tempo far beyond our familiar sense of time. And within that rhythm, each of us, along with every star, every galaxy, is just a brief spark within a long cycle. That spark does not exist to shine forever, but to play its part in the ongoing flow of space. When viewed this way, existence becomes lighter, and the mystery of the beginning becomes part of a continuous chain, rather than a solitary, isolated question. Yet even here, the story does not end. The cyclic Ekpyrotic universe is only one path toward answering the question, what came before the Big Bang? Another model arises from a completely different direction, not from branes or collisions, but from the idea that spacetime itself has a quantum structure, like a delicate lattice that can be compressed and then rebound. That model comes from loop quantum gravity, and it opens an entirely new way of imagining the birth and rebirth of the cosmos. Here, our journey gently shifts toward another vision of the Big Bounce. Quiet, profound, and as calm as the breath of space itself. As the idea of a cyclic universe continues to drift softly through the mind, like a cosmic breath stretched across trillions of years, another quiet question begins to surface beneath the current of thought. If branes can collide, separate and collide again to form the rhythm of cosmic birth and death, is there another way to understand this repetition that doesn't rely on higher dimensional membranes at all, but instead on the very structure of spacetime itself? Could spacetime be more than a smooth, continuous canvas? Could it possess its own microscopic structure, its own limits, its own ability to be compressed and then spring outward like a coiled spring? This idea does not arise from strings or branes, but from a very different theory, an independent attempt to unify the largest and smallest scales of nature, loop quantum gravity. And at this gentle turning point, our story steps into a new landscape, where spacetime is no longer a silent stage but a fabric woven from tiny quantum threads. Loop quantum gravity, or LQG, is a bold approach in the quest for a unified theory. Instead of assuming that everything is made of vibrating strings, as string theory does, LQG begins with a deeply fundamental question. If matter and energy are quantized, could spacetime, the arena in which they exist, remain continuous and smooth? Or might spacetime itself be quantized, broken into unimaginably tiny units? LQG chooses the latter, and from that choice emerges an entirely different picture of reality's foundation. According to LQG, space is not a smooth surface. If we could shrink ourselves down far enough, past atoms, past particles, past all known fields of energy, we would find that space is not empty at all, but a dense network of quantum loops, tiny rings woven together like a lattice. Each loop is on the order of 10 to 35 meters, millions of trillions of times smaller than a proton. These loops resemble the threads of a fabric. From far away, the fabric appears seamless. Up close, it reveals countless fibers intertwined. If spacetime is a fabric woven from loops of energy, then every point in space is a meeting place of these loops. Smoothness disappears. In its place is a faint, shimmering grain, microscopic architecture hidden from ordinary perception. And it is these quantum loops that determine how space curves, how gravity behaves, and how the universe evolves through time. A remarkable shift occurs when we apply this idea to the entire universe. This is the domain known as loop quantum cosmology, LQC. When the quantum network of LQG is brought into cosmological equations, the familiar formulas of general relativity begin to change under conditions of extreme density. No longer does matter compress to infinity as the universe contracts. Instead, when the universe reaches the maximum density that the quantum fabric of spacetime can allow, a special quantum force appears. This force is not gravitational attraction. It is a repulsive force, one that halts the contraction and pushes space outward. Imagine this: the universe shrinking, heating, tightening. In classical relativity, nothing stops this collapse, and a singularity inevitably forms, a place where the laws of physics shatter because quantities blow up to infinity. But in LQG, as the universe contracts, the quantum threads of spacetime become compressed to their limit. When they can no longer be squeezed further, they rebound like a spring. Gravity no longer pulls inward. It reverses, becoming a pushing force. That moment of rebound is the Big Bounce. In the view of LQG, the Big Bang was not a creation from nothing. It was the expansion phase following a previous universe that had been contracting. The prior universe never plunged into a singularity. It simply shrank to the smallest size permitted by the quantum structure of spacetime, then bounced outward, unfolding into the universe we inhabit today. This picture carries a unique kind of beauty. Instead of a terrifying, infinite point, the universe becomes a gentle motion, contracting, reaching a minimum, and springing outward. Imagine the entire fabric of spacetime shrinking, and at the limit of compression, the quantum loops woven within it suddenly stretching back out, creating a surge that expands the universe. No breaking, no fragmentation, just a soft transition. Not an ending, but a turning point. And this leads to a profound conclusion. If LQG is correct, the Big Bang was not the absolute beginning. It was simply the moment when the contraction of a previous universe turned into the expansion of our own. Time stretches smoothly before and after the Big Bang, unbroken by singularities. Before our universe existed, another universe preceded it, and before that one, perhaps another. Each cycle follows not from collisions, but from the quantum structure of space-time itself, which forces the universe to rebound when compressed too far. Thus, from the breathing of the cyclic Brane universe, we now shift to another rhythm, the breathing of space-time itself. A different story, arising from a different direction, yet leading us toward the same calm idea. The universe did not come from nothing, but from a long, gentle sequence of transformations between contraction and expansion. As this chapter closes, another quiet question rises. If LQG provides a mechanism to prevent singularities and create a big bounce, what comes next in the story? What was the universe like before the bounce? Are there traces left behind? These ideas await the next chapter, where we step into the story of the Big Bounce itself within quantum cosmology. As the ideas about the quantum structure of spacetime continue to resonate softly, a gentle realization begins to emerge. If spacetime itself can be compressed to its ultimate limit and then spring outward again, then this mechanism must do more than describe the microscopic nature of the universe. It might also recount the entire history of the cosmos. In the previous section, the notion that tiny quantum loops could resist the universe's collapse opened a new door. A universe that never sinks into a singularity, but instead rebounds once it reaches a certain threshold. And as that idea grows, spreading into a quiet, natural question, we begin to wonder, if spacetime can rebound, could the Big Bang, the event that gave birth to everything, simply be the universe's springing back? From here, the story glides gently into the Big Bounce model, a different way of understanding our origins, where the Big Bang is no longer an absolute beginning, but a moment of transition between two cosmic cycles. In the Big Bounce picture within Loop Quantum Cosmology, LQC, the universe does not emerge from nothing. It does not rise out of a perfect void, nor does it explode from a point of infinite density. Instead, our universe is seen as the result of something deeper, a previous universe that once expanded to great size and then slowly contracted under the pull of its own gravity. As gravity took the lead, that universe began its retreat, folding inward like a sphere being compressed. But even as everything was squeezed tighter and tighter, as temperature and density climbed with every moment, the universe could never fall into a singularity, because the quantum structure of space-time forbids it. Picture a universe shrinking so much that stars and galaxies lose all distinction. And deeper still, where space itself is woven from countless quantum loops, compression becomes impossible. When all of space-time reaches the maximum density allowed by its quantum fabric, a new kind of pressure appears. Not the pressure of matter, but the elasticity of space-time itself. That pressure grows until it completely overcomes the inward pull of gravity. When the balance finally breaks, the universe rebounds, shifting from contraction to expansion. In the Big Bounce model, that moment of rebound is the Big Bang as we know it. In essence, the Big Bang and the Big Bounce are two views of the same event. The Big Bang is no longer the first moment many once imagined. Instead, it becomes a note in the middle of the cosmic symphony, the end of the contraction chapter, and the beginning of the expansion chapter. Seen this way, before our Big Bang, there was another universe, slowly collapsing. And it is entirely possible that the universe before that one was itself born from an earlier bounce. A long, unending chain, a cycle of rebirths, without any need for higher dimensional branes as in the Ekpyrotic model. Here, everything arises simply from the quantum microarchitecture of spacetime. To picture it more easily, imagine a soft rubber ball. As you squeeze it, the ball gets smaller, but only to a point. Beyond that limit, the ball pushes back harder than you push in, and it springs outward. The Big Bounce works the same way, but on the scale of the entire universe. The old universe is compressed to a quantum limit, then springs outward, giving birth to a new one. No infinities, no absolute boundaries, only continuous, gentle transformation, yet profound enough to reshape our entire understanding of how everything began. One especially intriguing aspect of the Big Bounce is the possibility of searching for traces of the previous universe within our own. If a prior universe contracted and then rebounded, the features of that contraction might leave subtle patterns in the cosmic microwave background, CMB. Some theoretical models suggest there could be tiny scars or signatures, minute variations in the CMB or special gravitational wave signals, acting as whispers from the universe that came before. Though none of this has been confirmed yet, the search itself brings a romantic beauty to science, as if we are listening for the fading echoes of a universe that once existed before us, carried across a quantum rebound and still faintly present in the sky. The Big Bounce also carries a quiet sense of optimism. Instead of viewing the universe as something that began from nothing and moves toward an uncertain future, the Big Bounce tells another kind of story, a story of resilience. The universe is continually squeezed, continually pushed to its limits, yet each time it rebounds, giving rise to light, matter, galaxies, and eventually life. A cosmic phoenix takes shape, a universe reborn from its own ashes. There is no final ending, only transformation, and with each cycle comes the possibility of a new beginning. As this idea spreads, the story becomes not only scientific, but softly poetic. The universe is not a straight line with a beginning and an end. It is a vast spiral, where existence flows through subtle rises and falls. Nothing truly disappears. Everything simply shifts form, just as a ball is pressed in and springs back out. As this section closes, a delicate thought appears at the edge of reflection. If the Big Bounce explains how our universe was born, might we find traces of earlier cycles within ourselves? And that story, those clues, will lead us into the next journey, where science tries to listen for the distant echoes of the universe before the Big Bang. As the idea of the Big Bounce lingers, like a quiet stream flowing through awareness, a natural question slowly rises. If the universe once contracted and then sprang outward, if a previous cosmos left a silent note in the long symphony of spacetime, could we, in this present universe, still sense its echo? Could an ancient past, lying beyond the boundary of the Big Bang, have left faint traces in the very sky we look up at? From here, our journey slides gently into a new terrain, the realm of observation and verification, where extraordinary hypotheses are laid beneath the light of data and delicate measurements, and where science, though still without a final answer, continues to widen its curious wings. In modern physics, the Big Bang is understood not only through theory, but through the fossil light left over from the early universe, the cosmic microwave background, or CMB. The CMB is the oldest light we can observe, released when the universe was only a few 100,000 years old. Its subtle temperature variations have been measured with astonishing precision, and those fluctuations have confirmed many cosmological models. But more intriguingly, within those patterns of temperature, there may be hints of a story that unfolded before the Big Bang. Some researchers have proposed that if our universe is one bubble in a wider multiverse, as suggested by eternal inflation, then our bubble may once have bumped into another. Such a collision, if it happened, could leave a signature in the CMB, concentric circles with temperature shifts slightly different from their surroundings. These rings would resemble ripples left behind when two droplets touch upon a still pond. So far, analysis from the Planck and WMAP CMB maps has not found definitive evidence. Yet the very search opens a horizon of wonder. Perhaps the night sky carries the gentle afterglow of another universe, a soft touch that occurred before our own time began. Beyond the CMB, another source of information comes from gravitational waves, ripples in the fabric of spacetime created by immensely powerful events. If there was ever a phase of contraction and rebound, or if spacetime underwent a deep transition of energy, that process could have produced primordial gravitational waves. These waves, if they exist, would have a unique frequency signature, distinct from those generated by black hole mergers or neutron star collisions. Observatories like LIGO have already marked a turning point in the study of gravitational waves, and future projects such as LISA will be far more sensitive, capable of sweeping for signals from epochs earlier than any light could ever reach us. If we were to find a gravitational wave pattern consistent with Big Bounce predictions, or with a cosmic bubble collision model, it would become one of the strongest pieces of evidence for a before the Big Bang. It would suggest that the universe was not born from a singular point, but from a deeper transition shaped by quantum law. Alongside grand signals like the CMB and gravitational waves, physicists hope for subtler hints as well. One possibility is the detection of exotic particles, such as magnetic monopoles, hypothetical particles predicted in certain early universe models that might be tied to transitions preceding the Big Bang. If monopoles were ever discovered, they could indicate that our universe carries remnants of a pre-Big Bang reality. In a similar vein, some dark matter theories propose that dark particles may have formed through quantum processes that occurred before the universe entered its fiery expansion. Yet for now, no direct evidence confirms the Big Bounce, nor any specific hypothesis about what came before the Big Bang. Every proposed signature, from concentric CMB circles to early gravitational wave patterns, needs more testing, more data, more care. But this is not discouraging. On the contrary, it highlights the quiet endurance of science. Science does not merely seek answers, it cherishes the journey of seeking. Each time scientists point a telescope toward the sky, or refine the sensitivity of gravitational wave detectors, or simulate a universe before time itself, they are trying to listen for the faintest murmur coming from the farthest past humans can imagine. They are touching the edge of cosmic history, the place where everything began, or perhaps where everything transitioned into a new cycle. In the stillness of the night sky, these questions do not feel heavy. They sparkle gently, like small stars shimmering at the edge of our awareness. Each star is a possibility, a hypothesis, a path leading toward the origins of the universe. And even without a final answer, the search continues. Quiet, patient, enduring. And at the intersection of science and wonder, we realize something. Sometimes it is the pursuit of questions beyond human reach that makes the universe beautiful. Not knowing is not an absence. It is an open door, a doorway into endless possibilities. And from that pre-cosmic realm, the story will carry us into the next part, where we reflect on the meaning of this entire journey as the search for pre-cosmic traces fades, like a distant wave dissolving across a quiet lake. Another feeling begins to rise. Not urgency, but a contemplative stillness. For when we stand before things as elusive as mysterious circles in the CMB, unshaped whispers of gravitational waves, or exotic particles hovering at the edge of prediction, we are not only examining data, we are also looking into our own desire to understand. And from that place of intersection, our journey shifts into a wider space, the space of meaning, where science touches the boundary of the wondrous, and the wondrous illuminates the way we look at science. From the beginning of this story until now, we have wandered through many landscapes, cosmic bubbles born in an endless sea of inflation, hidden dimensions curled into strange threads, delicate three-dimensional brains drifting through 11-dimensional space, universe sparking collisions between those brains, and finally the breathing rhythm of the Big Bounce, a cosmic life stretching across innumerable cycles. Each hypothesis we visited is like a fragment, incomplete, uncertain, but shimmering in its own way, forming a broader mosaic of the before universe. And when we step back and look at those fragments, we realize that it is not the answers they offer, but the diversity of possibilities that makes the question worth pondering. The quiet message all these theories whisper to us is, our universe may not be unique. It may be only one bubble in an endless multiversal sea. It may be one of countless states in the vast string landscape. It may be the result of a collision between two brains, or a quantum rebound from an older universe. It may be woven into a chain of cycles, each cycle a different expression of reality, yet all connected by the subtle shifts of spacetime. And when we open ourselves to all these possibilities, something beautiful emerges. Science is not only a process of finding truth. Science is a meeting place between imagination and reality, between ambition and humility, between what we can measure and what we can only dream about. Those intricate models, from the multiverse to the Big Bounce, are achievements of human intellect. But they are also reminders that we are always reaching towards something beyond ourselves. And in this moment, we may gently ask, will we ever know for certain what happened before the Big Bang? The most honest answer is perhaps not, or perhaps not yet. But it is this uncertainty that makes the journey so profound. If everything were clear, the universe would lose some of its shimmering mystery. It is the absence of a final answer that keeps us looking up, keeps us measuring, keeps us asking, keeps us expanding the boundaries of what we know. There is something deeply human in all of this. When a child looks up at the night sky and asks, "Why are we here?" that question is not just curiosity. It is a primal instinct of awareness, hundo, the echo of thousands of generations who once stared into the dark and searched for connection with something larger than themselves. Questions about the origin of the universe, no matter how difficult, belong to that ancient tradition, the tradition of minds that know how to wonder. Because of what we don't know, we are reminded of how small we are in the vastness of the cosmos. Because of the mysteries left unsolved, we learn humility. And through journeys like this one, our minds expand, allowing us to feel the beauty of the world not only in everyday moments, but in things far beyond our direct experience. In this moment, when hypotheses, models, and data settle gently like slow-falling snow, we may sense something else: gratitude. Gratitude that the universe is vast enough for us to ask questions for a lifetime and still stand nowhere near its edge. Gratitude that our understanding is limited, but our curiosity is not. Gratitude that in an endless, boundless cosmos, there is a small place where we can lie down, close our eyes, and let our minds drift with these stories. The journey to the before universe was never a quest for a destination. It is a journey of expansion, of intellect, of imagination, of emotion. Sometimes we don't need to know the answer to appreciate the beauty of the question. And as this section comes to a close, the story will ease into its final part, a gentle ending that guides us towards sleep with the feeling that even if we may never know what happened before the universe began, we can still rest in the embrace of the universe we have now, a universe that has carried us for billions of years, and will continue whispering its wonders into the last dreams of this night. As our journey brushed against its final reflections in the last section, where we realized that the unanswered question itself is what weaves the universe's beauty, a gentle feeling begins to spread. Like stepping out of a long dream while still holding a trace of its diffuse glow, the mind drifts into a softer, more open space. And from that softness, the ending of our story appears quietly, like an invitation to step into the most peaceful corner of the cosmos, where mystery no longer unsettles us, but becomes something we can hold close. Throughout our journey, we've traveled through countless ideas. We've soared across the oceans of cosmic inflation, where space expands so quickly that time feels like a passing breeze. We've glided among drifting universe bubbles floating like giant dewdrops in an endless multiversal sea. We've visited hidden dimensions that human imagination rarely touches, leaving behind a kind of wistfulness, like opening a door to a world tucked behind the thin curtain of reality. We've witnessed majestic collisions between cosmic brains, where energy flares like the spark that awakens a sleeping universe. And afterward, we saw another picture, gentler, quieter, the universe contracting like a deep breath, then springing forth again in a moment of rebirth. The Big Bounce, a cycle without light but full of hope. All these things are not just theories, they are pieces of a cosmic fairy tale, woven from human intellect, curiosity, and a longing to touch our origins. And when we look back across this whole journey, what emerges is not an answer, but a feeling. A feeling that is hard to name, small yet immense, facing the vastness, yet somehow held by it. For the universe before the Big Bang may forever remain a mystery, and yet that is precisely what makes it beautiful. Mystery is not an emptiness. Mystery is richness. Not knowing becomes its own form of understanding. The understanding that we live in a world larger than we can grasp, and that this is something wonderful. In this moment, let your mind drift like a speck of stardust, floating among faraway galaxies. Imagine the place where you are lying, the place where you are breathing, the cells in your body carrying out their quiet work, all of it connected to a history older than any memory humanity has ever held. Every atom in your body was once part of a star, forged in supernova fire, pressed within dark clouds of interstellar gas. It was once light, once heat, once time. You are, in a very real way, the universe made visible. And because you carry that story within you, you also carry the ease of accepting what remains unknown. Let your thoughts drift past the stars, slip past galaxies spinning like slow disks of light. Let the idea of countless other universes, where light may have different colors, where physics may follow different rhythms, settle like a soft cloud in your mind. You don't need to understand it. You don't need to answer it. You only need to feel the quiet beauty of not knowing. There is something magical about accepting mystery. The mind becomes lighter. Freed from the duty to pin down a single conclusion, you can let each question drift by like a breeze, cool enough to refresh, distant enough to soothe. And in that stillness, you realize that the quest for knowledge is not a race. It is a lullaby, slow, gentle, where each beat is a reflection, and each breath a tiny discovery. And now, as the story reaches its final notes, let everything settle. Let the thought that the universe has held you for 13.8 billion years become a warm blanket across your mind. From the moment the first atoms emerged after the Big Bang, to their journey through stars, clouds, and cosmic wanderings, until they finally became part of your body. The universe has always been beside you, No light in tonight's sky is a stranger. All of it is the distant kin of the particles that made you. So as you drift into sleep, feel that embrace. Imagine yourself resting in the arms of the universe, not as a small creature swallowed by vastness, but as a piece gently returning to the whole that created it. A return that is soft, quiet, without questions, without worry. Before you close your eyes, hold on to one last thought. Perhaps in your dreams, you will travel to the place where everything began. Maybe you will brush against a newborn cosmic bubble, or glimpse the early shimmer of a quantum bounce. And no matter what you find there, let yourself smile, because the journey matters more than the destination. Because beauty lives in the steps we take, not in the finish line. Sleep well in the arms of the infinite, where every question can become a star, and every dream can be a new beginning.